Hello, we are back. Today we're going to talk about solutions, and we're going to start by first introducing the idea of what it means to have things dissolved in water. If you think about your typical covalent compound, like sugar, here's a representation of a particular sugar, glucose. If you look at this sugar, you can simply dissolve it in water, either by adding water to it or simply adding the solid to the water, shaking it a little bit. And in essence, what happens is that the water, once it comes in contact with the solid, can engage in interactions that pretty much involve this OH bond that you see either in the sugar molecule or the water molecules themselves. Specifically, notice the lone pair of water interacting with the hydrogen of the OH bond in the molecule, and conversely, notice the OH bond of water interacting with the lone pair on the oxygen within the sugar molecule. So this entire interaction is what we call hydrogen bonding, and it's a fairly strong interaction. It's not strong as the covalent bonds themselves, but it is a strong interaction that allows the water to kind of sequester each individual molecule of sugar away from each other. So it's no longer a solid, now it's interacting with water and it goes directly into the solution to the point that to you it looks like you only have one thing. Whenever this happens, we call this an aqueous solution. We use the symbol AQ to denominate it. And this is not exclusive to covalent molecules. You could also do this with ionic compounds. And the ionic compound that I'm going to choose right here is, it could be anything that's really soluble, like manganese 2 chloride. You could start with that solid. You could add it to water. And what happens is now that the ionic substance becomes completely solubilized. It gets dissolved in water. With the formula, we just represent that by putting the AQ symbol. But the reality of it is that the ions get separated as the interaction with water commences. And here you can see the cation, the manganese 2 plus cation, interacting with water molecules, creating what we call coordinated covalent bonds. And this whole structure is simplified by just writing the ion, the metal with its charge, and the AQ symbol. And then we have the chlorides, which are also separated from the cation, and they are interacting with water in a very similar fashion as what you saw with the covalent molecule before. But these are stronger interactions because now you have the lone pair of electrons, which are negatively charged, interacting with a full positive charge, and the hydrogen portion of the OH bond of water interacting with a full-on negative charge. So this is in essence what needs to happen for ionic compounds to fully dissolve. They separate into corresponding unique ions. And so even though you started with one molecule of manganese 2 chloride, you end up with 3 separate ions present in the same solution. We refer to these ions as electrolytes. And the reason for that is because they can serve the conduction of electricity very well. So think of the soluble ions as electrolytes. They're kind of synonymous with each other. Okay, so now that we kind of have an understanding of what it means to dissolve things into water, now we're going to do a few calculations. We're going to introduce the idea of concentration. And simply put, concentration, when you look at your typical solution, you have a substance that is dissolved in water. That substance is referred to as the solute. And by definition, the solute is a substance that is present in the least amount of moles. The substance that you dissolve the solute into, in this case water, is referred to as the solvent. And it is the substance present in the greatest amount of moles. Together, the solute plus the solvent are referred to as the solution. Okay? And one can actually determine and express the quantity of solute that has been dissolved in your solution by something we call concentration. And in this class, we're going to simply represent it in two forms. There's actually many other forms of concentration out there, but we're only going to be studying two of them. So yes, we will see how much solute is present in the solution, and we're going to start with molarity. The molarity concentration, which is often abbreviated as capital M, is defined as the moles of the solute this divided by the volume of the solution. Okay, not the volume of the solvent, but the volume of the solution itself. And specifically, it's moles of solute over liters of solution. The percent mass by volume, which is another way of defining concentration, is simply given by this percent, and in parentheses m over v to emphasize that this is mass per volume. It has a similar attribute. You divide the mass of the solute by the volume of the solution, and since it's a percentage, you multiply by 100. So let me show you how we actually do calculations with this. We have in this example 10.7 grams of glucose, and in parentheses here I'm giving you the molecular mass or molecular weight of the solute, 180.16 grams per mole, and we're basically dissolving this in enough water to make up 250 mLs of solution. So we're going to calculate the molarity and the percent by mass volume for this entire solution. So we start with the quantity that only has a single unit associated with it, in other words, the 10.7 grams. All right, and I'm going to use this table to kind of keep track of all the components. All right, so the mass is directly given for us, the mass of the solute to be most exact, 10.7 grams. Okay, we also know the volume of the solution, so under solution and volume we have the 250 mLs. For molarity, we're going to need to change it to liters. So if you move the decimal point 1, 2, 3 positions to the left, which is the same thing as saying, divide the volume in mLs by 1000 mLs to change it to liters, we can, have it expressed as 0.2500 liters. All right, now, volume of solute we're not going to need for finding molarity or percent by mass concentrations. Neither are we going to need the mass of the solution or the moles of the solution. Those parameters are needed for other types of concentrations, but since we're not dealing with them in this class, we're going to keep it blank. One thing we're going to need, however, is the moles of the solute. So for that, we need to start with the mass of the solutes, the 10.7 grams of glucose, and we need to carry out a conversion. We have grams of glucose on top, so we're going to need to have grams of glucose on the bottom. And on top, we have the other unit, which is the moles of glucose, right? So in essence, we're using the molecular mass of glucose to do the conversion from grams to moles. And as you may recall, the number always goes with the first unit. The second unit just has 1 as the placeholder. So 180.16 needs to go where the grams go, which in this case is the denominator. And then this is equivalent to 1 mole. So the grams per glucose, or grams of glucose, will cancel out. You'll end up with just moles. So if you divide 10.7 by 180.16, you'll get the moles of glucose. And so we can enter that in here. Okay, so now that we have that table pretty much complete, we can now calculate the molarity and the percent by mass. So let's start with molarity. Right, so we need to introduce the moles of solute, right, which is the 0.0594 moles, and we're going to divide this by the volume of solution in liters, so 0.2500 liters, and we carry out that division, and upon doing so we find out that this number ends up being equal to 0.238 moles per liter, or capital M for as an abbreviation. We also refer to this thing as molar concentration, 0.238 molar concentration. Okay, now for the same solution we can express the concentration additionally in terms of percent by mass volume. So we're going to do that. We're going to enter the mass of the solute, which is the 10.7 grams. We're going to divide by the volume of solution, and this time around we want the volume to be in mLs. So we're going to enter 250, not 0.25 but 250 mLs, and this gets multiplied by 100%. So when we divide 10.7 by 250, pressing enter on the calculator and then follow that up by multiplying by 100, we find out that this equals 4.28. And they both represent the same concentration for the same exact solution. It's just two ways of looking at the same thing. Okay, so this leads us into the idea that because concentrations are actual ratios, they can be used as conversion factors. And so I'm going to show you another example where we can actually use the concentrations themselves as conversion factors. So in this problem, we're going to do a little bit of conversions involving molecules, which we'll talk more about in upcoming lectures, but we're going to let the units guide us through the process. So here we go. we have 25.3 grams of silver carbonate. I'm giving you the molecular weight of silver carbonate right next to it. And we actually obtain that much silver carbonate upon reaction of 0.245 molarity concentration of silver nitrate with 0.5 molar sodium carbonate. And what I want to find out is what the volume in mLs of both silver nitrate and sodium carbonate needs to be to generate the actual yield of silver carbonate. So to start this problem, what I personally like to do is first have the balance equation, right? So I'm giving you the balance equation here from the get-go. In due time, you will have to predict some of these products. You will have to balance the reactions yourselves, and then you can proceed with what I'm going to show you now. So we have the concentration of silver nitrate, which we said is the 0.245 molar. So I'm putting it in here. Instead of saying molar, I'm just spelling out that's moles per liter. The same thing goes for sodium carbonate. The concentration is 0.5 molar or 0.5 moles per liter. And then for the product, the silver carbonate, we know that the mass that we obtain is at 25.3 grams, and the molar mass is 275.75. So this is everything that we have right here. Actually 74, but it's okay. That won't make much of a difference. All right, so what we do is we start with that amount. Out of all the numbers, what you should notice is that there's only one number that has just a single unit associated with it, and that's the 25.3 grams of the silver carbonate, right? Everything else has dual units, which implies that those are going to be conversion factors. All right, so if we start with this, we have grams of silver carbonate, so we're going to place grams of silver carbonate on the bottom, and we can switch from mass to moles, so we'll place the moles on top. And this means that we're going to have to use the molar mass of silver carbonate, right? So we'll introduce the 275.74, so actually here I use the correct number, so we're good. And then for the mole, we only need 1 mole, right? So the grams will cancel out. You'll end up with moles of silver carbonate. And now here's the deal. You're not actually interested in the volume of silver carbonate. What you want to find out instead is the volume of silver nitrate and sodium carbonate. So here's where you have to really pay attention to the balancing coefficients of your balanced equation, because what we're going to do is we're going to switch from the moles of silver carbonate to the moles of silver nitrate, at least initially. And in order to do that, we have to take notice that there is 2 silver nitrates for every 1 silver carbonate present. So those are literally the values that we're going to place right here. Now this is something that really you can only do once you are in units of moles. You do not want to do this when you're still dealing with grams or volume. You need to be in moles to basically be able to switch from one substance to another. So this will cancel out the moles of silver carbonate, and now we're dealing with moles of silver nitrate. So now we made a switch. Okay, so now that we're in silver nitrate, now we can actually use the molarity of silver nitrate, because notice this has units of moles per liter. Right now we're dealing with moles of silver nitrate, so we need to put moles of silver nitrate on the bottom, and on top we'll have the liters of silver nitrate. And since the first unit of molarity is the moles, that's where the number will go. So the 0.245 needs to go on the bottom, and on top we have 1 liter. But since we're going to go after mLs, we can change the 1 liter to 1,000 mLs automatically. Or alternatively, you could create a new conversion factor to switch from liters to mLs. This is totally up to you. Okay, but this will do the trick. Everything cancels out except for the mLs of silver nitrate. So first we divide 25.3 by 275.74, press enter. Multiply by 2, press enter. Multiply by 1,000, press enter. Divide by 0.245, press enter, and you should find out that this equates to 749 mLs of silver nitrate. Okay. Now we're going to do the same thing now for silver carbonate, and in fact, this is going to look very similar to what we did right here up until the second conversion. So the first conversion is the same thing. You go from mass of silver carbonate to moles of silver carbonate using its molar mass. You get rid of the grams of silver carbonate. Then you switch from moles of silver carbonate to moles of sodium carbonate. And notice that the balancing coefficients are 1 to 1 in this reaction, so you only need 1 mole of each to make the switch. The moles of silver carbonate will cancel out. You'll end up with moles of sodium carbonate. And then, using the molarity of sodium carbonate, we can switch over from moles of sodium carbonate to mLs of sodium carbonate, right? And once again, I did the little switch directly that 1 liter is equal to 1,000 mLs to just get to that final unit. And so we do the same thing. We divide the initial mass by the molar mass of silver carbonate. 1 and 1 don't change anything. Then we multiply by 1,000. We press enter. We divide by 0.5. Press enter. We find out that this equates to 184 mLs of sodium carbonate. So to put it in simple terms, to make 25.3 grams of silver carbonate, you're going to need to at least add 749 mLs of silver nitrate of a concentration of 0.245 molarity, and you're going to need to combine it with 144 mLs of sodium carbonate of half a molar concentration. Okay, so with that, we have finished this first part of the videos. I hope this helps you with the conversions. We'll have more to say about this type of problems in future lectures. So consider this a bit of an introduction, but be mindful that the key idea right here is that you can switch from volume to moles using molarity, right? It can be a conversion factor in and of itself. Okay, so in the next video, I will show you how to do further calculations that involve dilutions, and we'll talk about osmosis. So I'll see you in the next video.